vector integration. So in this vector integration we have three theorems, so integral theorems. The first one is Green's theorem, next one is Stokes theorem, and then the third one Gauss divergence theorem. So we have three theorems in this vector integration. Now we have the statement, we have only statements of theorems, no need for the proof of these theorems. The first theorem, Green's theorem in a plane. What will be the statement? So if C is a simple closed curve enclosing a region R in the xy plane, and P xy and P of xy and Q of xy and first order and its first order partial derivatives are continuous in R, then integral over C P dx plus Q dy equal to, so double integral over R dou Q by dou x minus dou P by dou y dx dy, where C is described in the anti-clockwise direction. Suppose so these are closed curve C, right, which enclose some region R. So in this there are two functions P and Q, and its first order partial derivatives are continuous in this region. Then we have this statement, integral over C P dx plus Q dy equal double integral over R dou Q by dou x minus dou P by dou y. So this result is true. We have to verify this result. Okay, so that is our using that we can application of this Green's theorem. Sometimes you have to evaluate the integrals, and sometimes you have to find out the area of this region. We can apply this Green's theorem to find out the area of this type of regions. Clear? Now listen here, see this problem. So verify Green's theorem in a plane with respect to integral over C x square minus y square dx plus 2xy dy, where C is the boundary of the rectangle in the xy plane bounded by the lines x equal to 0, x equal to a, y equal to 0 and y equal to b. By you have to verify the statement. What will be the statement of the Green's theorem? So by statement of Green's theorem, so integral over C P dx plus Q dy equal, so double integral over R, so dou Q by dou x minus dou P by dou y dx dy. So this is the statement of Green's theorem. So I have to verify this result, right? Now C is the boundary of the rectangle. So what will be the rectangle? Bounded by, so this x-axis and this is y-axis. This one is y equal to 0 and this is x equal to 0. And then x equal to a line parallel to y-axis, and then y equal to b, a line parallel to x-axis. So this is anti-clockwise direction. So this is the C. So you can mark it. So O, A, B, C. So this is a closed curve C. It encloses the region rectangle R, right? So now I'll take the right hand side. What is, I compare with this left hand side with the given integrals, integral over C x square minus p square into dx plus 2x by dy. You compare it, what is P and Q? So we have here P equal to x square minus y square and Q equal to 2xy. So on the right hand side we need dou Q by dou x minus dou P by dou y. You differentiate partially with respect to y. So dou P by dou y equal to minus 2y, and then dou Q by dou x equal to 2y. Right? Now we have to take the right hand side. Just you have to evaluate the right hand side of this theorem. So double integral over R, so dou Q by dou x minus dou P by dou y dx dy equal to, so double integral over R, so dou Q by dou x is 2y and minus, so 4y dx dy. How we can evaluate this double integral? So in this region either you draw a vertical strip or horizontal strip. So I can take our horizontal step. So x varies from 0 to a, and then y varies from 0 to b. So we can write this. So integral 0 to b, then 0 to a, 4y dx dy. So now we have to integrate this. So the question is, so x varies from 0 to a and y varies from 0 to b. If the region is rectangle or square, we can write it like this. So 0 to b, so integrate with respect to x, so keeping y as constant. So 4y into x, so 0 to a into dy. So you can take a outside, so 4a integral 0 to b, y into dy. So integrate this, so 4a into y squared by 2, 0 to b. We'll simplify it, so 2a b squared. So take it as this equation number 1. The right hand side of the given integral is 2a b squared. Now we go for the left hand side. So integral of c p dx plus q dy equal, what is c here? C is the closed curve described in the anti-clockwise direction. So here C is the boundary of the rectangle. What will be the boundary? So OA, then AB, then BC and CO. So this C can be split into integral over OA p dx plus q dy plus integral over AB p dx plus q dy and integral over BC p dx plus q dy plus integral over CO p dx plus q dy. So this point is 0, 0, and this one is a comma 0, this one is a comma b, this one is 0 comma b, right? This point. Right. So now we take the first one. So what is p here? So p equal to x squared minus y squared and q equal to 2xy. So this is the result we have that. So p dx plus q dy. So along OA, what is OA? So this OAB, this C is anti-clockwise direction. This one is y equal to 0, this one is x equal to a, y equal to b, and this is x equal to 0. So along OA we have y equal to 0, right? So y equal to 0 implies dy equal to 0. So p dx plus q dy equal to, so p, what is that, x squared minus this one is 0 into dx, then dy is 0, so obviously this is 0. So x squared dx. So integral over OA p dx plus q dy equal to integral over OA x squared dx. So in this line OA, x varies from what? OA, x varies from 0 to a. So integral 0 to a x squared dx. So integrate this, x cubed by 3, 0 to a. This is equal to a cubed by 3. Next, along AB. So along AB, you have x equal to a. So dx equal to 0. And differentiate point is 0. So p dx plus q dy equal, so x squared minus y squared into dx plus q is 2xy into dy. So this is p dx plus q dy. You have this result, x equal to a and dx is 0, so this is 0. So x equal to a, so 2ay dy. So integral over ab p dx plus q dy equals integral over ab, this one is 2ay dy. So here the variable is in y, so in the line AB, y varies from, so this one is a comma 0, so 0 to b. So this is equal integral 0 to b 2ay dy. So integrate this, so 2a into y squared by 2, 0 to b, so ab squared, right. Now along BC, so along BC, what will be the equation? Y equal to b, so which implies dy equal to 0. So we have p dx plus q dy equal to y equal to b, so x squared minus b squared into dx, and this one is 0. So integral over BC p dx plus q dy equal to x squared minus b squared into dx. In the line BC, x varies from a to 0, right? BC ங்கிற லைன்ல b ங்கிற பாயிண்ட்ல a ஓட x ஓட வேல்யூ a, c ல 0, so a to 0. So this is equal integral a to 0 x squared minus b squared into dx. So integrate this, so x cubed by 3 minus b squared x, so a to 0. So substitute upper limit 0 and minus a cubed by 3 plus a b squared, right. And then the last one, CO, along CO. So along CO, x equal to 0, so dx equal 0. So p dx plus q dy equal to x squared minus y squared into dx plus 2xy into dy. You put x equal to 0 and dx equal to 0. So this is 0 and x equal to 0 is also 0. So therefore integral over CO p dx plus q dy equal to 0. Now you substitute this 4 result in this equation. You have so along OA, the answer is a cube by 3. Then along AB, AB squared. Then along BC, minus a cube by 3 plus AB squared. Along CO, this is 0. So add these 4 results. So you have 2a b squared. So this is equation 2. So from 1 and 2, so we have equation 1 and so w integral over r dou q by dou x minus dou p by dou y dx dy equal to 2ab square. Proof so that's equation 1. So from these two results we have, what is that? The left hand sides are equal. So integral over c p dx plus q dy equal to double integral over r, so dou q by dou x minus dou p by dou y dx dy. Right, so hence we verified the Green's theorem statement. Next problem, so verify Green's theorem in a plane for integral over c 3x squared minus 8y squared into dx plus 4y minus 6xy into dy, where c is the boundary of the region defined by the lines x equal to 0, y equal to 0 and x plus y equal to 1. Then what will be the statement of Green's theorem? Integral over c p dx plus q dy equal to double integral over r dou q by dou x minus dou p by dou y dx dy. Now c is the boundary of these lines. So this is x-axis and this is y-axis. So x equal to 0 is the line y-axis, and y equal to 0 is the line x-axis, and x plus y equal to 1 is a straight line where it cuts the x-axis and y-axis is 1, 0 and 0, 1. So this is the region R, and there is a boundary of the C. So take it as OA, B, O. OA, B, OA, B, O. So that is a C. So C is anti-clockwise direction. Okay. So now we have P equal to 3x squared minus 8y squared, and Q equal to 4y minus 6xy. We take the right hand side, so dou P by dou y equal to, we differentiate with respect to y, so minus 16y. So dou Q by dou x equal to minus 6y. So double integral over R, dou Q by dou x minus dou P by dou y dx dy equal to double integral over R. So this one is minus 6y, and minus this one is minus, so plus 16y into dx dy. So where R is a rectangle, triangle like this, so you draw a horizontal stream. So this one is x plus y equal to 1. So x varies from 0 to 1 minus y. So x varies from 0 to 1 minus y, and y varies from 0 to 1. So you move the strip from bottom to top, so y varies from 0 to 1. So 10y dx dy, right? This is equal to 0 to 1. Then with respect to x, keeping a y as constant, into x 0 to 1 minus y into dy, and 0 to 1, so 10y into 1 minus y into dy, so 0 to 1, so 10y minus 10y squared. So integrate this, 10y squared by 2 minus 10y cubed by 3, 0 to 1. So this is equal to 10 by 2 minus 10 by 3. So 5 minus 10 by 3, so 15 minus 10, so 5 by 3. So we take it as equation number 1. So now we go for the left hand side, so integral over C P dx plus Q dy. So here C is the boundary of the triangle, so OA, AB and BO, which is equal to integral over OA plus integral over AB plus integral over BO P dx plus Q dy. Okay, so first you take along OA. So along OA, y equal to 0, so dy equal to 0, so P dx plus Q dy equal to, so P is so 3x squared minus 8y squared into dx, then Q plus 4y minus 6xy into dy. You substitute in this, so e equal to 0 and dy equal to 0. So this is 0 and this is 0. So 3x squared into dx. So integral over OA P dx plus Q dy equal to integral over OA 3x squared dx. So in this line OA, x varies from 0 to 1. So 0 to 1, 3x squared dx. So 3 into x cubed by 3, so 0 to 1, so 1. Now along AB, with the line AB, x plus y equal to 1, so y equal to 1 minus x, then dy equal to minus dx. So we substitute in this P dx plus Q dy equal to 3x squared minus 8 into y squared, 1 minus x the whole square into dx. plus 4 into 1 minus x minus 6x into 1 minus x into minus dx. Simplify it. So 3x squared minus 8 into 1 minus 2x plus x squared. Then take minus here. So minus 4 into 1 minus x minus 6x plus 6x squared into dx. So simplify it. 3x squared minus 8 plus 16x minus 8x squared minus 4 so plus 4x and plus 6x minus 6x squared into dx. Simplify it. So 3x squared minus 8x squared, so minus 5x squared. So here minus 6x squared, so minus 11x squared. And then 16x plus 4x, 20x plus 26x. Then minus 8 minus 12 into dx. Therefore, integral over AB p dx plus q dy equal integral over AB minus 11x squared plus 26x minus 12 into dx. Along AB, so x varies from 1 to 0. 1 to 0. So integrate this, so minus 11x cubed by 3 plus 26x squared by 2 minus 12x. So 1 to 0. Substitute upper limit 0, then minus lower limit. So plus 11 by 3 minus 26 by 2, then plus 12. Now minus 1, 8 by 3. Yeah. Now the last one along BO. So along BO x equal to 0. So therefore dx equal to 0. So p dx plus q dy equal to. So these put x equal to 0 and dx equal to 0. So this is 0. Then 4y dy. So integral over BO p dx plus q dy equal to integrating along BO, the y varies from 1 to 0. So 1 to 0, 4y dy. So 4y squared by 2, 1 to 0, so minus 2. Upper limit 0 and lower limit 2, so minus 2. So therefore, we substitute in this result. So OA is 1, then AB is 8 by 3, then minus 2. So 8 by 3 minus 1. So it is equal to 5 by 3. So from 1 and 2, so we have integral over C p dx plus q dy equal to double integral over R qx minus py dx dy. So the Green's theorem verified. Right. So now I have to prove that the area bounded by a simple closed curve C is given by 1 by 2 into integral over C x dy minus y dx. So by a statement of Green's theorem, integral over C p dx plus q dy equal to, so double integral over R dou q by dou x minus dou p by dou y into dx dy. So here there is a closed curve C. It enclosed a region R. So area of this region R is nothing but there is a 1 by 2 into integral over C x dy minus y dx. Okay. So now you take this result. So integral over C x dy minus y dx equals. So compare these two. So this is Q and this is P, right? So W integral over R dou Q by dou X. So Q is X. So dou by dou X of then Q is X minus dou by dou Y of P. What is P? Minus Y into dx dy. We multiplied 1 by 2 on both sides. So 1 by 2 into integral over C x dy minus y dx equal 1 by 2 into W integral over R dou by dou x of x is 1, dou by dou y of this, so minus into minus plus 1 into dx dy. So these two to get cancelled. So W integral over R dx dy. Multiple integral. W integral over R dx dy is nothing but what? This is nothing but the area of region R. Right? By using Green's theorem, area is nothing but what? 1 by 2 into integral over C x dy minus y dx. In general, so W integral over R dx dy is the area of the region, right? Okay. So using this result, we can find out the area of the circle x square plus y squared equal to a square. So x square plus y squared equal to a square, a circle with center, origin, radius a, right? So this is C. This one is x square plus y squared equal to a square. So axis and y axis. Then area equal 1 by 2 into integral over C x dy minus y dx. So we know these are results. X equal a cos theta and y equal a sin theta. So we have x squared plus y squared equal to a squared. A circular equation. What is dx? Minus a sin theta into d theta. Then dy equal a cos theta into d theta. So here 1 by 2 into integral over C x, so a cos theta into dy is a cos theta into d theta, then minus y is a sin theta into dx is minus a sin theta into d theta. Then take d theta outside. So 1 by 2 into this theta varies from, the circle theta varies from what? 0 to 2 pi. So integral 0 to 2 pi. So a squared cos squared theta plus a squared sin squared theta into d theta. So you can take a square outside. So 1 by 2 into a square integral over 0 to 2 pi. So cos squared theta plus sin squared theta 1 to d theta. So a squared by 2. So theta 0 to 2 pi. So a squared by 2. So 2 pi. So pi a square. So this is what? Area of the circle with radius a is pi a square. Right? Okay, next is this application of this Green's theorem. So using Green's theorem, so I have to evaluate this integral where C is the boundary of the square formed by x equal to plus or minus 1 and y equal to plus or minus 1. So this is x axis and this is y axis. So x equal to 1 is like this and x equal to minus 1 is this. and y equal to minus 1 and y equal to plus 1. So this is the boundary of the C. This is origin, right? So I'll take it as this A, B, C and D. So this point, this line is bound x equal to minus 1 and this line is x equal to 1, y equal to minus 1, y equal to plus 1. So using this Green's theorem, we have to evaluate this integral. So by statement of Green's theorem, integral over C p dx plus q dy equal to double integral over R dou q by dou x minus dou p by dou y dx dy. So integral over C, write on this, x squared into 1 plus y dx plus x cube plus y cube into dy. If this is equal to, I apply this results. Double integral over R. So dou by dou x of q. What is q? This x cube plus y cube. And minus dou by dou y of p. So there is x squared into 1 plus y into dx dy. So double integral over R with respect to x. So you may get 3x squared minus with respect to y you get x squared into dx dy. Solve with the limit. So x varies from minus 1 to 1 and y varies from minus 1 to 1. Take a horizontal strip. X varies from minus 1 to 1 and y varies from minus 1 to 1. So minus 1 to 1 minus 1 to 1. So 2x squared dx dy equal to integral minus 1 to 1. So this is an even function. So I can write 2 times 0 to 1 2x squared dx into dy. So I get 4 into minus 1 to 1. So integrate this x cube by 3 0 to 1 dy. So 4 into minus 1 to 1. So 1 by 3 dy. So it is also an even function. This is equal to 8 into 0 to 1 1 by 3 into dy. 2 times போடும்போது 8 ஆயிரும். So it take 8 by 3 into y 0 to 1. So this is equal to 8 by 3. So integral over C is equal to 8 by 3. Clear?